Katie Mack, thank you for joining us.
Thank you for having me.
It's great to have you here. Tell us why you're here now and why you're going to be here again soon.
So right now I'm officially a visiting fellow, but I'm coming to join the Perimeter Institute on a full-time basis starting in June.
We're very happy about that.
Thank you. Yes, I'm very excited about it as well. So I've been having a bunch of meetings with people and sort of sorting out details of the role. Yeah, it's gonna be great.
And what is this full-time role going to look like here at Perimeter?
So it's called the Hawking Chair in Cosmology and Science Communication, and it's a position that is going to be joint between cosmology research, carrying on my research program, and doing public engagement work and communication and working with the amazing outreach team here at Perimeter to bring physics to the public.
Well, we're very happy that you're going to be helping us with that because we love doing that.
Yeah.
Now, we're sitting here in the Stephen Hawking Center at Perimeter
Yes.
Institute. You're going to be the Hawking Chair.
Yes.
What's it like to have a sort of a position that's named after someone that you've not only sort of, I don't want to say, looked up to, I
Yeah,
almost said
yeah.
idolized, but also you've worked with. Can you tell us about what it means for you to have this title?
Yeah, no, it's, Stephen Hawking was the first person I ever knew of who was called a cosmologist, right? When I was a little kid, I read A Brief History of Time, and I was just amazed at all these ideas about the Big Bang and black holes and space-time and all of that. And so, I looked at Stephen Hawking, and his job was called cosmologist. I was like, okay, I'm going to be a cosmologist. That's what I want to do.
What age is this where you decided
I think I was probably 10. I was pretty
and here
young.
you are a cosmologist.
And I am a cosmologist, and I've encountered Stephen Hawking a couple of times in my career. The first time I met him, I was like 14 years old. He gave a talk at Caltech before I was even an undergrad there. I went because I lived in Southern California, and so I went and watched his talk, and afterward, sort of did a little fangirl moment, said hi to him and said I was an admirer of his work, and he said thank you very much, which is very exciting for me. But then when I was in grad school, I spent a year at Cambridge University working with people doing a research kind of thing, and I ended up giving a talk there where Stephen Hawking came to my talk, and that was
pressure.
that was one of the most harrowing academic experiences I've had. It's one thing to give a talk in front of your sort of childhood idol about a topic that he sort of pioneered. I was talking about primordial black holes, which was something he worked on very extensively. But it's another when he's heckling. So what happened was I went to give this talk. I was setting up for the talk, and all of these eminent professors were already sitting down, and then I was nervous because I thought he could show up, but he hadn't yet, and I was like, okay. And then I hear this like beep 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 as his wheelchair is coming in, and so he's set up in the front of the room. So I'm like, okay, I have to do this thing, and so I get started with the talk, and I introduce myself. I put up my title slide. I say I'm going to talk about primordial black holes, and I hear thank you. And I look at Hawking. I'm like, okay, and I kind of laugh.
You heard it in that iconic voice that everyone knows.
I kind of think like maybe it's a joke because I'm talking about primordial black holes and he worked on those, and I don't know. But everybody kind of chuckled, and then I moved on, and then I continue the talk, and at some point I hear no. And I'm like, what? And I look at him, and he's just like eating his lunch. The carer who's there, feeding him, is just kind of looking blankly at me. Like nobody is giving me any kind of clue what's going on here. And I can't ask him to repeat himself, because at that point he was using this machine that it took like 2 minutes per word. He couldn't. Yeah, he was
just using a cheek
this little thing that looks at the cheek. And he'd sort of wink to choose words. And so I just kind of paused and then carried on. And then throughout the talk, at various times I'd hear something like yes, or I don't know, or I don't think so. And I had to just keep going. I couldn't, and every time I would sort of respectfully pause and then move on.
But you did hear Stephen Hawking say, "I don't know," in a talk you were giving.
That is
That's
true.
gotta be something.
Yeah. I mean, it was a number of different little phrases. But then, so eventually the talk finishes. He goes off somewhere else. He didn't ask any questions. And then I asked the organizer, like, what was going on with Stephen Hawking? Like, what was he doing? And he was like, oh, his the little sensor that senses his cheek movement, it malfunctions when he's eating. so because he was chewing, it was just going through the quick select menu of phrases, yes, no, maybe, I don't know, I don't think so. Just the things that are easy to get to. And you can't turn it off because then he wouldn't have any way of speaking. So he just has these outbursts, and nobody told me.
Yeah.
I had no idea that was going to happen. I don't know if it was like a hazing thing. I was just a grad student. I didn't know what was going on.
Do you know what he eventually thought of the talk?
I don't know what he thought of the talk. I did talk to him once more about my research at a dinner thing, and he didn't really say much. I mean, he was very careful with his words. He didn't go off on tangents. He didn't say things unless he had a really good reason to. So we didn't end up having a real conversation. Although I was in the same research group sort of broadly as him, so I was around the stuff he was doing. I wasn't working directly with him, but it was still kind of, it was neat to be able to meet and interact with your sort of childhood hero.
And be heckled by him.
And be heckled by him. I mean, it made a great story to be able to survive that and just carry on. But
Just go back a little bit. Stephen Hawking was a cosmologist. You saw him when you were young. You said, I want to be a cosmologist.
Yes.
What's a cosmologist?
So a cosmologist is somebody who studies the universe sort of as a whole, or the fundamental physics of the universe. So I often explain it as the universe from the largest to the smallest scales from beginning to end. So anything to do with the bigger picture of how the universe works. So cosmologists study things like the Big Bang or the future of the universe. They study what the universe is made of, how it works physically, like what the laws are that govern the cosmos. And so I've worked in various areas around there. I've worked in the early universe and like what happened at the Big Bang, that kind of question. I work on dark matter, which is one of the most important components of the universe, but we don't know what it is. And I've also thought a lot about the end of the universe and just various aspects of like how does it work, what's really going on.
So nothing much then, just everything, just the whole universe.
Yeah, I was gonna say hearing your description, it seems just like such a broad field. I mean, you can study the past, the present, the future, the big, the small. Yeah. At any point in your career, how do you choose where to focus your attention?
I mean, I've been very fortunate in my career that I've had a lot of freedom to study what I'm interested in and to just kind of follow my curiosity. So I've had research fellowships where I'm not tied to a particular project, but I get to present, here's what I want to work on, and then I work on that thing. So I've just kind of looked at like what's the interesting question, where can I be really creative about this? So things like talking to the theorists about what the new sort of physical model is they're thinking about, like what's the big theory that everybody's excited about, and then talking to the observers about the new telescopes that they're going to build, like what is this new telescope going to see about the first galaxies in the universe or whatever, and then trying to find ways to bring those together, trying to find out, what can those telescopes tell us about those theories, and, what kinds of experiments do we need to test those theories, and that kind of intermediate stage where you get to learn about every aspect of these questions and try and find new creative ways to bring them together. So that's kind of the area I like to work in. But in terms of topic, it's anything from black holes to early galaxies to cosmic strings to dark matter to, microscopic black holes that might have started in the early universe, just all kinds of stuff like that, because there's some interesting creative way I can approach the question.
What's the interesting problem you're grappling with now, and what's your creative approach to it?
So I'm particularly interested in dark matter. So we know that most of the matter in the universe, most of the stuff that has mass in the universe, is totally invisible. We can't see it with ordinary light. It doesn't seem to reflect or emit light or absorb light. So it's hard to look at directly, but we can see that it's there based on how it affects things that are lit up in the universe, stars and galaxies.
I have a question.
Yes.
Is there any dark matter in this room? Is dark matter
Probably.
everywhere?
Yes.
Okay.
Yes. So there probably is
It's
dark
not just
matter in this
far
room.
away in space.
No,
It's
no. There's
permeating.
like about a third of a proton mass per cubic centimeter is roughly how much dark matter is around here, and it's moving through, passing right through us.
Yeah.
That's most likely sort of where we're at with dark matter. There's a lot of uncertainties in this.
And this makes up most of the universe.
Most of the matter in the
Okay,
universe.
right.
When I get to most of the universe, we have to talk about dark energy. It's a totally different thing, but most of the matter, yes. But yeah, so we're pretty sure dark matter is there. It seems to be important to the functioning of matter in the universe, to the growth of galaxies, to the formation of structure on the largest scales. But we don't know what it is, and there's a hope that maybe if dark matter particles, if they really are particles, which I think probably they are, if dark matter particles collide in just the right way, they might annihilate with each other and create regular particles like things like positrons and electrons or quark pairs or something like that. And if that's the case, then regions of really dense dark matter should glow with high energy particles that we can see, just to some tiny degree. And so a lot of people have followed that possibility and looked for evidence of dark matter annihilating in the center of the galaxy or in small galaxies nearby or various places like that. One thing that I've been interested in recently is what if that does happen? How would it have affected the first galaxies in the universe? So these clumps of dark matter where the first gas got together and formed stars and galaxies, how would those structures be affected by a little bit of energy coming out of the centers of these dark matter clumps? And then furthermore, if that is happening, how does that or if that did happen in the past, how does that change what we can see with radio telescopes and with infrared telescopes, things that can look at those first galaxies? So things like the James Webb Space Telescope, which hopefully will be launched by the time this podcast comes out. Hopefully it's up there doing great science. Now I'm getting nervous about it. Anyway, that telescope and other space telescopes designed to look for the very first galaxies, they might see something different if dark matter is annihilating in those first galaxies or if it's not.
So looking at the first galaxies, it sounds like that requires traveling back in time.
Yeah.
Is that when our telescopes look out really, really far, they're looking at things the way they were. Was dark matter around at the very beginning? Has it been around forever?
Yeah, I mean, as far as we can tell, dark matter was part of the sort of primordial soup of the very, very early universe, and was crucial to building up the first matter structures in the universe, the first galaxies, the first stars. It helped bring all that gas together and to allow it to form those first stars and galaxies. And we have some idea of kind of how that worked. We have a reasonably good idea of the fact that if dark matter were not there, then the gas that makes up our own galaxy, the Milky Way, would not have been able to come together enough to form the Milky Way as we see it today. So it's been a factor in the evolution of structure since the beginning. Whether or not it's been injecting high energy particles and photons, energy into these clumps, we don't know. And so that's what I'm trying to figure out. So trying to model what that would look like, how it would affect those first stars and galaxies, what you would see with space telescopes, what you see with radio telescopes that can sort of probe the neutral hydrogen that formed the first stars and galaxies at very, very early times. And it is great, as you say, these telescopes are time machines. You can look at the past. You can see directly things that happened in the first billion years of the universe. We're at 13.8 billion years now. We can see galaxies that were, before 500 million years, just very, very early in the universe. And of course, we can see the background light from the Big Bang itself, the cosmic microwave background. And we get clues about dark matter from all of that. And hopefully, we'll get some clues as to whether or not it does this annihilation thing when we start to be able to look at those first galaxies more directly.
Wow.
I'm curious, what specifically you're looking for with those telescopes. What is that evidence that helps you be more sure that dark matter played a role at different stages of the universe?
Yeah, so in terms of how it affects, like, just played a role gravitationally, how it brought matter together, the way you learn that is from modeling the gravitational growth of structure. So you do computer models to simulate matter coming together, and you see what happens if that matter coming together has pressure and like acts like gas where it can kind of puff up again, or if it's dark matter where it just has gravity and doesn't have pressure, it doesn't puff up. When you, like, if you let dark matter sort of fall toward itself, it's not going to bounce off, and it's not going to like kind of heat up the way that gas, if it falls together, it kind of gets puffy. So so you have different dynamics around how things grow through gravity, if it's dark matter or if it's regular matter. And so computer modeling is a big part of figuring out how dark matter affected the gravitational sort of development of these structures. In terms of how we'll know if it's annihilating or not, that's a different question. And that's also something where you have to do computer modeling to see where that energy goes within that dark matter structure, where it goes when it goes into the gas, and how that changes the physics of that gas, and how it changes, like, maybe what it does is it blows out all the gas in the smallest little clumps of dark matter, and so you can only form galaxies in larger clumps of dark matter, and that would be something you would be able to tell the difference in a sort of large survey with telescopes.
Now, you've mentioned that you look into the beginnings of the universe and the ends of the universe. It hasn't happened yet. Is looking at one sort of imperative for understanding the other?
I think that what we really want is a big picture of the whole evolution of the universe and the structure of the universe. And so the beginning is part of that question. How did the universe begin?
How did it begin? Tell us now. Hurry.
Well, we're kind of still working on that. Yeah. But yeah, the beginning of the universe is one part of that question, and the end of the universe is another part. And if you have a theory for the beginning of the universe, it generally has an implication for the end as well. And if you have a theory for the end, maybe it'll lead to a new beginning. There are some theories that have a sort of cycling universe. So they are kind of parts of the same question, because they're both asking about this kind of big picture question of what is the nature of the universe? Is it embedded in some larger, multiverse, or is there some part of the universe that's so far away from us it's not observable to us, and how does that affect the evolution of the universe? And if you really understand the beginning, you know if that beginning is the result of the end of a previous universe, for example. So there are ways that these things are connected. But also, we learn a lot about what the universe is made of by looking at the beginning of the universe, by looking at things like the cosmic microwave background, which is the light from the Big Bang itself, really. But it's also something that we can study carefully to learn about the components of the universe, because it encodes a lot of really important information. But if we know what the universe is made of completely, then that also helps us to extrapolate into the future of how those things will evolve in time. So for example, dark energy, which I sort of briefly mentioned, is some mysterious stuff that's making the universe expand faster all the time. And we don't know what dark energy is. But if we can understand the early universe and what was present in the early universe and how all the pieces fit together then and how it's evolved over time, then we can extrapolate into the future what dark energy will do and how it may or may not destroy the universe in the future.
And what kind of pieces are needed, do you think, to help understand what dark energy really is?
Well, dark energy is tough because, as far as we can tell, all it does is make the universe expand faster. It doesn't seem to interact with anything else in any other way. It stretches space, and that's it. So all you can really study with dark energy, as we understand it, is you can study the evolution of the expansion of the universe, how it's changed over time in expansion rate and so on. And you can study the evolution, the sort of growth of structure in the universe, so how galaxy clusters come together. And you can do that by looking at the past and seeing, watching kind of that growth happen. And that's kind of it. Like there are some theories about dark energy that involve things that could interact with experiments. And so people are really hoping to find some connection with an experiment with dark energy. But it might just be like a sort of aspect of the universe, that there's some number that designates how this expansion works, and it's just part of how, it's just written into the equations of gravity. That's called the cosmological constant. It's just an aspect of the universe that's got this sort of stretchiness in it, and it's also a challenge to understand, like, why that number, why does that term exist? We don't know.
So from hearing what you're describing about your work, it just seems like you're almost trying to put together a lot of pieces of the puzzle to talk about how we can go from the beginning to the end and everything in between.
Yeah.
From your perspective, what are the most interesting chapters of that story?
I think that it sort of on the timeline, the beginning and the end are, of course, the exciting bits. But in terms of like what we're trying to learn, I think the big mysteries, dark matter, dark energy are the huge questions. The Big Bang, there are a bunch of questions around that. Like, there's this idea of cosmic inflation that at some point very, very early on in the universe, after whatever the beginning was, tiny fraction of a second after that, there was a rapid expansion, and it sort of stretched out space to an extreme degree, and then that rapid expansion calmed down to the normal expansion, and then sort of the kind of hot Big Bang that we talk about, the sort of hot glowing plasma phase of the universe started, and then we got stars and galaxies and so on. We don't know if cosmic inflation happened or not. There's good reasons to believe it probably did, but there are also theories that are out there that involve not cosmic inflation, so something else that sort of set up the conditions for that hot Big Bang, and we don't know where to go with that right now, and it's difficult to study. It's difficult to get strong evidence either way, and we don't.
Newer telescopes help with that? Are we still getting further and further?
Well, yeah. So different new ways to observe the cosmic microwave background can help with that. So what we're looking for there is by looking at the sort of the details of the light from the cosmic microwave background, this first light in the universe, we might be able to see signs of gravitational waves in the very, very early universe. So this is sort of waves of space-time stretching. And if we can see evidence of those, then that can give us a clue that, yes, inflation really did happen. Mm-hmm. And back in 2014, we thought we did see that with an experiment called BICEP 2. Turned out we were fooled by cosmic dust, so we didn't see that. And there are experiments going on now, observations with new telescopes, hoping to actually see that signature, and that would give us a big hint. Mm-hmm. And there are other sort of indirect things that might tell us something about inflation, but it's hard because there's it's a process that it doesn't leave a lot of clues necessarily, and so there are a number of things that are very consistent with inflation having happened, but those observations are also consistent with a few other theories that involve different evolutions in the very early universe that led to this hot Big Bang phase.
Now, you wrote a book
Yes.
a year or two ago with the very uplifting title, "The End of Everything."
The end
and it was
of
about
everything.
the end of everything.
The end of everything, astrophysically speaking.
Astrophysically speaking.
Yes.
Thank you.
Yes.
Thank you for clarifying, because it would have been even more terrifying had you not. Tell us, why did you write a book about the end of everything?
Yes.
And
Okay.
can you tell us what are some of the ways that everything might end, astrophysically speaking?
Right. So, I think the reason I wrote about the end of the universe as opposed to, say, the beginning or something, is that for one thing, there were already lots of books about the beginning of the universe, and I didn't think that I needed to write another book about the beginning of the universe. But also, in my various studies in cosmology, I've frequently come across papers or talks that are about different ways the universe might end, and I'm always just fascinated by that question. And I notice that when I give public talks, the audience gets really excited about the question of the end, and I realize that it's just not out there in the public consciousness enough. Like, how do we think the universe is going to end? What are the possibilities? Mm-hmm. And it seemed like a fun opportunity to dig down on those and present like what we really know about the future of the universe now. What are the different possibilities? How are we distinguishing between them? And like, what's all the physics that sort of comes into all that. So it was really fun because I was able to bring in all of my favorite cosmology fun facts and little bits of interesting physics along the way, while also talking about this sort of big, scary destruction. And so I probably shouldn't laugh at the destruction of the universe, but it's
going to
hard.
happen way down the road, right?
Yeah, I mean, it's not an immediate fear, and yet it's so overwhelmingly huge that you kind of have to laugh, because like, what else are you going to do? Like the whole universe is going to be destroyed. Like, okay.
And if I'm right, one of your scenarios, that's not your scenarios. You're not the orchestrator of the end of the universe, but a chronicler of it. It could happen right now, right?
Technically, yeah.
Okay.
So technically, one of the scenarios, called vacuum decay, is something that would be triggered by a quantum event that is unpredictable, and you wouldn't know that it happened. And in principle, that could happen anytime, anywhere. In practice, like, based on what we think we understand, the timeline for that actually to occur is like 10 to the power of 100 years from now, something like that. Like, we don't know, because it's a hard calculation, and there's still a lot we're trying to figure out. I mean, we don't even know if the theory that suggests the possibility of vacuum decay is valid, right? It's the standard model of particle physics, which is this theory of particle physics that we've validated with experiment, but we know has some holes in it, and there's things that aren't explained by it. So, maybe vacuum decay will happen. Maybe it'll happen in 5 minutes. Probably not. And
I
it's
assume
something
you have to tell a lot of people. Probably not.
Yeah, I mean, I do, every time I talk about vacuum decay, I have to be really, really careful to say, please do not worry about this, because people do worry about this, because some people get very anxious about the idea of the universe suddenly ending, which on some level I can understand. But, like, you wouldn't even notice it if it happened, because it would happen so quickly.
And it happens to everybody at once.
And it happens to everyone at once,
Yeah.
or like in a sort of bubble of doom that expands the speed of light, and so it doesn't matter. Like, you can't.
Bubble
Anyway.
of doom.
Yeah, what is
expanding at the
that? What
speed
is a
of light.
bubble of doom?
Yeah, so when the quantum event occurs in one spot, it creates a bubble of a new kind of space called a true vacuum, and that bubble expands at about the speed of light, and therefore, like, you can't see it coming. And it just destroys everything immediately when it hits it. But anyway, the point is,
Don't worry.
don't worry, because you're nothing you can do about it. You wouldn't see it coming. Nothing would be left. You wouldn't notice it. And it's all, as I said, based on these ideas about the standard model of particle physics, where we know that there are missing pieces to that theory, and so we don't know which pieces may or may not, come into play in the real possibility of vacuum decay. And there are much more immediate things that we should worry about that are not like, a tiny infinitesimally small chance of happening in like 100 billion years, right?
Yeah.
So anyway, don't worry about vacuum decay.
Is there a more likely scenario that people billions of years from now should worry about?
Well, I mean, I think the most likely scenario, as far as what we know about the universe now, is something called the heat death, which is where the universe basically kind of fizzles out. Like, so we know the universe is currently expanding. We know it's accelerating in its expansion, and what's happening is really that galaxies are getting farther apart from each other, and everything is getting more and more isolated. And so if we follow that, extrapolate that into the future, in 100 billion years, every galaxy will be kind of on its own, unable to see other galaxies. In 100 billion years, if you put the Hubble Space Telescope up, it won't see anything.
Right.
It'll just be darkness out there. Like, you might see
Because
a few
everything's
lights in the Milky
expanding
Way.
away from everything else.
Yeah, I mean,
all
the Milky Way galaxy, by that time will have merged with the Andromeda galaxy, so there will be some stars still in our galaxy. Most of them will have died by then, but some will be around. And that's it. We won't be. All the other galaxies will be so far away from us, moving so quickly, we won't be able to see their light anymore.
And this is even if we have a major technological advance.
Oh yeah. No, this is a fundamental limit of the universe, that in 100 billion years we will not be able to see other galaxies.
Is it like how now we can only see so far until we can't see any further?
Yeah.
The observable universe ends,
Yeah.
and then whatever is past that. Do we have any idea what's?
No. I mean, we're pretty sure the universe continues more or less as it is past the edge of the observable universe, but we don't know. We have no direct information about about anything beyond the observable universe. So anyway, in the future, like in 100 billion years, astronomers, physicists will have no no evidence that other galaxies exist. They'll have no evidence of the Big Bang because they won't have any direct data about that.
That's under the assumption that there will be people around to make observations.
Right. Which
will
is,
our galaxy have smashed into
Yeah,
Andromeda in
yeah.
a catastrophic way or in a?
It depends on what you mean by catastrophic.
You have a different definition.
Yeah. I mean, most of the stars will survive when that happens. Like stars, even in a galaxy collision, stars don't hit each other.
Right.
Generally, there's a lot of empty space. But there'll be new bursts of star formation. Not a whole lot in that collision, but some. So a few things might get fried by supernovae. And the supermassive black holes in the centers of the galaxies will merge, and that could create jets of radiation that might be hazardous. But basically, it'll be fine. But
That should be the subtitle of your book. It'll be fine.
it'll be fine.
Yeah.
Yeah. But of course, the Earth will be long dead by then.
See,
Because
that's the spirit.
because the sun only has about 5 billion years more of burning hydrogen. And even before that, in only about 1 billion years or so, it'll get so hot or so bright, and it'll expand a little bit, and it'll boil off the oceans of the Earth, and the Earth will become uninhabitable. So, maybe we'll live somewhere else. I don't know, but the Earth will not. Humans will not be on Earth. We can
And
say.
is there anything that can happen after the end of the universe? Like in this vacuum decay situation, there's this new vacuum. Can anything come out of that?
So unfortunately, based on what we understand of the new vacuum, I'm sorry.
I love that you're laughing as you tell us all this bad news about our future.
So once you're inside the new vacuum, the true vacuum. So first of all, your atoms like dissociate because you have new laws of physics in there, and you don't have like electromagnetism anymore. So that's bad. But also, it turns out there's a calculation in 1980 suggesting that the new vacuum is gravitationally unstable, and so once you're inside and you've been dissociated, you also collapse into a black hole.
Oh.
So sorry.
That's the way I've always wanted to go.
Yeah, there's an amazing paper by Coleman and DeLucia from 1980 that goes through this process and that explains that this collapse will probably happen, and they have this wonderful paragraph about how you might have had hope that after the new vacuum there'd be new constants of nature and not only is life as we know it is impossible, so is chemistry as we know it impossible. But you might have had some stoic comfort from the fact that perhaps in the course of time, the new vacuum would sustain, if not life as we know it, at least some structures capable of knowing joy. And then they say this possibility has now been eliminated.
Great.
It's like, oh man.
I'm curious. You've looked at the universe in its entire lifetime so far, and then some. Where do we sit now in the age of the universe?
Yeah, that's a great question. So it depends on, so if we're assuming that the heat death is where we're headed, where, after you stop being able to see other galaxies, then the universe continues to expand and all the stars burn out in our galaxy and matter decays, and you end up with, black holes, and the black holes evaporate, and then you're just like sort of like this cold, dark, empty universe. If that's where we're headed, then on time scale, we're at the very beginning because because the amount of time that takes to get to that sort of end stage is like you're putting exponents on exponents on exponents. Like it's really like they're not good words for the number of years that you'd have to write down.
So we're
that.
roughly at 14 billion since the beginning now.
Yeah. And it's like
that's dwarfed by the time ahead.
Yeah. It's 100 billion before we just stop being able to see other galaxies, and then trillions and trillions and trillions and trillions onward before the black holes evaporate, and then onward and onward before you get to what you would call the end, the true heat death. But if you judge by how much has happened, we're almost at the end. Okay, so if you can calculate how many stars have formed in the universe, the rate of star formation in the universe, right? And it depends on a lot of things. And one of the things it depends on is how often galaxies are colliding with each other and coming in to mix their gas and form new stars that way, right? And so as the universe is expanding, galaxy collisions are happening less often, and starbursts are happening less often. And so we can look back and we can say, somewhere somewhere around like, I think it's like, I don't know, 6 or 7 or 8 or 9 billion years ago, there was way more star formation, and it's been declining since then, right? And you can work out that like of all the stars that ever formed in the past or that ever will form in the future based on our evolution, about 90% have already happened. So, from now until the end of time.
Does the universe
just-
just get kind of more boring and spread out from
Yeah.
now on?
Yeah.
Oh, great.
Yeah, and just the last 5 or 10% of stars are going to form. But all the others have already been born and are either burning or died.
Yeah.
So in that sense, we're almost at the end. So I don't know. I mean, it depends on whether you
You
want
still
to.
seem so optimistic.
Yeah, I mean, it depends on whether you want to think about, how much time you have or how much is going to happen. But
But these are timescales that boggle
Right.
anyone's.
Yeah, I
Like, how do
mean-
you even? What's the term? Vertigo. Cosmic
vertigo.
Cosmic vertigo.
Yeah.
When your mind reels at the
Yeah.
scales and the time scale of the size.
Yeah, I mean, it's you can't really. I mean, I don't know. Maybe some people can, but I can't really hold those numbers in my head in any meaningful way. I mean, this is why you use scientific notation for everything. 10 to the 11 years or like that kind of those kinds of numbers, because you have to try and think sort of in factor in, powers of 10, or you just it's meaningless. I mean, even like. Conceptually, I know that a billion is 1,000 times as much as a million. But in my head, it's like, that's about twice as much, right? Like, no, it's not.
Billionaires are much richer than millionaires.
Yeah, like to an absurd degree.
Yes.
But I, my own sort of conception, it's like, oh, so there's a million and then there's a billion, and it's like, it's about twice, but no. And so like,
I'm glad
I
to hear
still
you
have
do that
to.
too.
Yeah, so I still have to remind myself that these are you when you're trying to think in a logarithmic scale, you're not really conceptualizing it. You just have to kind of trust the numbers and try and sort of fake the intuition. I mean, again, maybe some people can hold those numbers in their head, but I really can't.
And talking about these different scenarios where the universe might end, would you be able to put any odds on what percentage you would say it's going to be this heat death versus something else?
I mean, I think I'd put bigger, pretty good odds on the heat death. I'd say, I don't know, maybe like 80% or something like that. There are other possibilities. So we don't know what dark energy is. And the idea of the heat death depends on dark energy being a cosmological constant, where it's just a property of the universe. It has this stretchiness built in. It's just, that's a thing that the universe does. Dark energy could be something that's dynamic, that changes with time, that's a sort of field in the universe that has a behavior. And if that's the case, then it could do anything, right? It could get more powerful over time, and that would lead to something we call the Big Rip, where not only are galaxies isolated from each other, they're also torn apart from the inside, and then stars are destroyed in atoms and nuclei, and you just tear apart the whole universe.
So violent.
Yeah. So that one's unlikely for some reason. I mean, there's theoretical reasons to not favor that idea, but the data can't rule it out just yet. And then there's the Big Crunch, which is something that they used to think in the 60s was most likely, where in the Big Crunch, the expansion of the universe stops and reverses, and everything kind of comes back together. And we don't think that's likely now because the expansion is accelerating. But if dark energy is something that can change and turn around, it could collapse the universe again. So, because we don't know what dark energy is, we don't know which of those possibilities might happen. And then there's cyclic models, models where the universe ends one way or another and then starts again. And, we don't know if those might have happened. And there are some reasons to believe that there are sort of advantages to those models versus like an inflationary early universe. Because you can set up the initial conditions of the universe differently if you have a previous cycle to draw from. So the cyclic models could give you something else, and those could end with something like a heat death or something like a Big Crunch, depending on what's governing that cycle. So there are other possibilities, but I would if I had to bet on it, and if I thought that it would ever I'd actually ever see the result of that wager, then I would probably put it on the heat death.
I want to ask, a lot of people may know you not so well as Katie Mack, and even better as Astro Katie.
Right.
How and when did Astro Katie become a thing on Twitter, and how did it's now, I don't know how many
Yeah.
followers you have, but
A lot. Yeah.
astronomical numbers.
Yeah, I think it's around 400,000 or something now. I don't know.
And that's just when we record, not when
yeah.
we're airing this.
That's true. Yeah, who knows? Maybe they'll all wander off. It's.
Oh, I meant it would grow, not.
Yeah, no, I know. But you never know. You always wonder. Like dark energy, you don't know which way it'll go.
Might turn around.
Yeah. Yeah, so I started on Twitter when I was in grad school, and I chose the name Astro Katie just as like something I wanted to throw in, astronomy, in my name. I don't know. It just seemed like a reasonable choice. But I started it just as a way of kind of like Twitter was new. I wanted to see what people were doing. And then when I was a postdoc, I saw one of my colleagues was using Twitter to talk about physics, to talk about astronomy. And I thought that was a really interesting way to do things. And he would do things like he would live tweet a conference and, like just a little like one tweet per talk or something about what was going on in conference. And I thought that was a cool idea. And at some point, I was visiting, he was based at Oxford. His name was Phil Marshall. He was based at Oxford at the time. And I was at Oxford to attend a conference, and he was also at Oxford, but he couldn't make it to the meeting. He was like, oh, can you live tweet this for me? And I'm like, okay. So I live tweet the talks, and he got a bunch of his followers to, he retweeted my stuff to a bunch of his followers. So it started there. So it started really just talking to other physicists and astronomers and a few sort of non-scientists who just enjoy following physicists and astronomers. And then it just kind of snowballed, like I would tweet more and get more followers through retweets and stuff. And then it just, and it compounds. And there were a few times when I would tweet something that would go kind of viral, and then that would give me a huge chunk of new followers. But
can you think of the first time you had where at Astro Katie had like a viral moment?
Yeah, I mean, the biggest one was when I was tweeting about climate change, and somebody who doesn't believe in climate change replied to my tweet saying, "Oh, this is a big scam. It's a hoax. You should go learn some science."
Oops.
And and I said, well, I don't know, man. I already went and got a PhD in astrophysics. I feel like more than that would be overkill. And it was just like, I was just like amusing myself by replying to this guy. I didn't think anybody would see it. I wasn't trying to make a big thing. I wasn't quote tweeting him or whatever. It was just a nothing reply. But people saw it and started sharing it and started retweeting it and talking about like, oh, this is a smackdown or what. And like I just wanted
to answer a guy.
Yeah, I was just kind of amused, making a little joke to myself for this. Anyway, and it just got super viral, and I went from 40,000 followers to 80,000 in like a week. And then a bunch of like minor internet celebrities started following me, and then J.K. Rowling tweeted a screenshot of it on her feed, and that got a bunch of followers. And then like it just kind of became this thing. And
it seems like you've rolled with it though, because it's an outlet for you to share science.
I mean, and so it's been great. Like I really like Twitter because I don't talk just about science. I mean, I talk a lot about science on Twitter, but I also talk about what's going on in the world, and I make jokes about random things and share funny images or whatever. But it's a way for me to both talk about science and get immediate feedback on that, like have conversations, answer questions. That's really valuable as a science communicator, to see what people are interested in, see what people are confused about, see, how different metaphors work and stuff like that. But then also I can present myself as a scientist who is not a science robot, right? And I think that's really valuable as a science communicator, to show that just because I'm, a physicist doesn't mean that like I only ever think about physics and I have nothing else going on in my life. Because the sort of media perception of scientists is, these incredibly cloistered, like single-minded people who don't know how to interact with humans, and I think that's a harmful stereotype for a number of reasons, and I think that it's helpful for a lot of things for scientists to be more visible, be more obviously human. Like it's a very important, I think, role to play. And so Twitter allows me to do that. It allows me to give people an insight into what's going on in my life, what I care about, and it gives me a platform for advocating for things I think are important as well. So when I tweet about politics or whatever, part of that's because like people listen to me, and I want to get ideas out there that I care about. And I don't think that's a contradiction. I think it's sort of intentional oversharing in terms of like, I want people to see me as a human with lots of different facets, not just representing physics,
Right. Well, one of the previous times you and I hung out was at Space Camp in Huntsville, Alabama.
Yeah,
and that was at a conference full of science communicators who are doing it through social media, through YouTube, really creative ways. Like when you started to get momentum on Twitter and got connected to all these other science communicators, was that sort of the impetus for, I want to do this? Or had you always thought, I want to communicate this science?
I mean, I think the way I got started into communicating science in general is just that I get really excited about things, and I want to share that excitement. And I think it's just an abundance of enthusiasm that causes me to want to tell everybody about like, this amazing thing I learned about, how orbits work or whatever. And also I've done a lot of writing, so I've always been somebody who's done a ton of writing. When I was, little, I used to write stories and letters and poems and stuff like that. And then I got into science writing as a freelancer through grad school and postdoc years, writing articles for newspapers and magazines. And so I just love communicating about the universe and sort of sharing what's exciting to me, what's really fascinating, like helping people to have those insightful moments. That's just hugely fun for me. And so I think, Twitter is part of that. Twitter helped me a lot in developing my understanding of like how to explain things in a simple way.
In a very small space.
Yeah,
and I have a question about that because I've heard a lot of researchers say, and I really agree, that giving a long presentation is a lot easier than giving a short presentation and I find that really challenging when I have to give a 15-minute presentation on my work. You have to take out all these details that are maybe not necessary to the fundamental point, but figuring out what those are is really not easy. And so I think writing a tweet where you're really limited in how much you can share is kind of the ultimate challenge. So how do you face that, and how do you decide what details to share, what details the public needs to know, whether it's about science or some of these political issues, whatever it is?
Well, I mean, it got a lot easier when they went from 120 to 240 characters. So that's one thing. I mean, I think that it's also possible now on Twitter to do long threads, and so that also takes away some of the pressure. But mostly, it's about trying to like, it's hard. I mean, I don't think there's like a quick, easy method. But you have to think about like the wording. So it helps to be really good with sort of a mental thesaurus to be able to choose really compact words to express the same idea. But then also you want to give a mental picture. Maybe that's through an analogy, or maybe it's through helping someone to visualize something. You want to give someone like something to connect to personally, one way or another. And how to do that, like, it just depends on what you're talking about. But yeah, it's super hard. And even longer form stuff. I mean, I used to write for Cosmos magazine, which is a magazine in Australia, a science magazine, kind of like Discover in the US or something. And I had a column with them, and it was like 700 or 800 words, and I'd write every couple of months. And I could write about whatever I wanted. At one point I decided I wanted to write about Noether's theorem, which is this idea that there's a connection between conserved quantities and symmetries of nature. And explaining what those two things mean is incredibly difficult. And I won't try and go through it now because it's actually really hard. But this is an idea that's really, really fundamental in physics, like the idea of symmetries in general, the idea of, if you change something about an equation, what is it that changes about the physics or doesn't, and how is that important? And, does the experiment work the same forward or backward in time? Does it, is there rotational symmetry? Like all these kinds of things are just super fundamental to how physics works. And so I wanted to explain that. And it took me like 2 months to get that into 700 words in a way that was understandable by somebody who has no physics background. And, it's just some of those concepts are super, super hard to explain simply. And it's just a matter of like practicing and sometimes you do need extra words. Like I couldn't compress Noether's theorem into a tweet in any way that would be, giving meaningful information. But it's a really fun challenge. Like I really enjoy, it's like putting together a puzzle or I enjoy that challenge of trying to find a way to explain something that gets the idea across simply and accessibly without being wrong. Because it's very easy to give like a bad answer that's short. And people do that. A lot of times science communicators will do that. They'll use a metaphor that's not a perfect metaphor, but they won't make it clear that it's not a perfect metaphor, and then people get confused and it's a whole problem. So being, trying to give the right amount of detail and make it clear what you're brushing under the carpet and what you're not. Like it's just hard, but it's something that if you have a ton of practice because you're on Twitter every day, you get better at it.
And science communication and outreach is going to be a part of what you're doing here
Oh,
at
yeah,
Perimeter.
yeah.
Can you tell us why you wanted to take on this role?
Yeah, I've been very fortunate in my career to have opportunities to do both research and public engagement in various ways. As a postdoc, it was a little bit harder because I was really just being evaluated on my research, and the outreach was sort of my nights and weekends job. But when I started at NC State, where I'm currently a professor in the physics department, that job was explicitly written as a job for a public scientist, somebody who does science and also interfaces with the public one way or another. And there's a whole group of us, the public science cluster, people who are connecting with the public in different ways through either their research or disseminating their work in some way. And so going into that job, I was explicitly given the freedom to do public engagement as part of my tenure package and all of that. Like it wasn't going to be a detriment to my advancement in the job. And they gave me some extra time by reducing the teaching that I was doing. And so that's been hugely helpful. And that's, that allowed me to write a book before tenure, which is something that most people do not attempt to do if they're in the physical sciences. And so when I started talking with Perimeter about this job here, I already knew how that balance could work well, and I really wanted to find a way to continue, these two things that I'm really passionate about: doing my research, trying to actually contribute to the discoveries and the development of the field, and also sharing everything with the world, and sharing my enthusiasm and helping people to understand physics. And so fortunately, we were able to put together a role for me here that really does both of those things, where I get to have, the same research support as any other researcher here, and also, explicitly use part of my time to connect with the public, to connect with the media, to be a sort of public face of the research side of the institution, and that's super exciting to me. I love the idea of both working with the amazing people in both of those groups, both cosmology and the public engagement side, and also representing perimeter science to the media or the public or whatever when it's possible to do that. So. Yeah, I'm thrilled about it. I think it's going to be an amazing job. Thank you.
We're thrilled as well.
Yeah.
We do have some questions that were submitted by people other than us.
Okay.
Yeah.
You want to
Yeah, we have
take
some.
the first one?
Sure. Yeah, there's some graduate students here at
Okay.
Perimeter that sent in some questions. So
Awesome.
the first one is a written question sent in from Barbara, who's a PhD student here. She asks, if you could know one thing, anything you want, what would it be?
I would want to know how the universe began. I would want to know if inflation really happened, if there was ever a singularity, how that came about, I guess that's asking a lot, but like I really want to know like what set off the universe, what set off the Big Bang.
If you had to take a guess today, we won't hold you to it.
If I had to take a guess, oh
Was
my
there a
gosh,
universe before the Big Bang? Was there nothing?
I don't know.
That's okay. It's an unfair question. I know it requires a lot of research and math, but
Yeah.
I thought I'd just ask you.
I don't know. I mean, I guess there's. I think I like the idea that the the universe came from nothing and there was some kind of singularity and then the inflation period and then the hot Big Bang. And I mean, I kind of aesthetically I kind of like that idea. I don't know. I can't support that on physics grounds because we just don't have that much information about that. But it's a neat idea. I don't know. It's a good question. But anyway, I want to know. That's what I want to know. That would be, more than even, like, it'd be great to know what dark matter is. I think we'll figure that out. We may never know what the first moment was. So if
How
I
did
could
the
know that, I
universe
would want to
begin?
know
That
that.
seems like a good question.
Yeah.
Yeah, that's great. And our next question is from Anna, who's a student in our PSI master's program. I think you met with her.
met Anna,
actually.
yeah.
Has the process of communicating science and the scientific method to the public changed the way you actually do your own research?
Oh, that's a great question. Yeah, I mean, I think it definitely has changed what I work on to some degree. So there have been various times when I mentioned that a lot of what I do is I talk to the theorists, I find out what they're excited about, I talk to the observers, I find out what they're excited about, and I try and make connections. And there have definitely been times when, because I was excited about something to share it with the public or like give a talk on it or something like that, I learned more about a topic and then used that information in my research. So there's definitely been times as somebody who's really trying to do big picture science, like really trying to, like cosmology in general, you have to know a lot of things about a lot of different topics. And then the area I work in, it's helpful to have that big picture, helpful to know what a lot of different people are doing and what the big exciting things are. I think that it's an area where talking to the public a lot is good because it really forces you to read more broadly and to talk to more people and get that big picture. And so certainly the public engagement has changed like what I work on to some degree, just by giving me sort of more tools, more information. In terms of if it's changed how I work, I don't know. I think that's hard to say. I think maybe it changed. It's probably changed like how I write my papers to some degree. It certainly changed how I give talks.
Yeah?
Yeah, I used to give talks with way more words and equations and bullet points, and now it's way more pictures. Just because when you give a talk to a public audience, you get used to the fact that you can't just put a bunch of words up there because it's distracting, and people will try and read while you're talking, and you can't communicate well that way. And I realized that actually that also applies to to professional talks, to research talks. Like unless you're really going through the information on the page as you go, people are not gonna, like, it's just gonna distract people. So I use more pictures, I do more explaining, I bring information on more slowly because of the experience I've had with the public where, I've just learned a lot more about how people absorb information.
Yeah, that's amazing. Okay, and our last question is from another PhD student named Nitika here at Perimeter. She asks, what would you like to share with students who are entering your field of research?
What would I share? I mean, I think that as a student and as a PhD student especially, it can get very lonely and very stressful. Right? There are times when it's just a hard field to be in. I mean, academia in general is just it can be, sort of mentally, emotionally hard. And I think that the pieces of advice I would give to people who are embarking on something like that would be, try and like look after yourself. Like don't sacrifice your mind and body to the field. Like try and stay healthy as much as you can and get sleep if you can, and like really look after your well-being, so that it's not so it doesn't like destroy you, so you don't burn out and
Have you had to
get
learn
sick.
that the hard way? Have you pushed yourself too hard?
Of course, yeah. That at times. And then also, you're going to be around a lot of people who are really smart and doing really amazing things, and you can't just like constantly be comparing yourself, and there's everybody feels levels of inadequacy when getting into physics, and that is a normal feeling, but also it's important to remind yourself like you really do know stuff, and like try and maintain that sort of enthusiasm and excitement about the field. I mean, for me, one of the ways that I dealt with that when I was going through my academic career was to do a lot of public engagement, because like when I'm around my colleagues, a lot of times it's like, oh, I feel like I'm the stupidest person in the room. Like I can't keep up or whatever. Like everybody has those feelings, but you can get caught up in that mindset. But then when you go and talk to a general public audience, like so much more about the topic than they do. And so people will come up to you and they'll be like, wow, that's amazing. You're really smart. And you're like, oh yeah, I know some stuff. and I mean, it's really good
Imposter
for like,
syndrome is context dependent.
Yeah. So it's really good for keeping up the morale, And the thing about imposter syndrome specifically, so the idea behind imposter syndrome is like, the idea is that you're really not good enough, but you fooled everyone and they're going to find you out someday. Right? That's the sort of the mentality that you get. I mean, my approach to that is like if you really think that you're an imposter, like just keep doing what you're doing because it's going great. Like, you're doing way better than you ought to be. Like, so just keep doing that.
Until you get heckled by Stephen Hawking, just assume that you're doing everything right.
I mean, yeah, it's obviously going super well, much better than it should be, and you just go with that. As long as you can, like milk it. So that's I try and keep that perspective on imposter syndrome.
If you could travel back in time to give yourself advice, would it be the same advice?
I would tell myself those things for sure. It depends on how far back I get to travel.
Big Bang.
Well,
initial conditions.
There are a lot of things I would change if I could go back to the Big Bang. No, I think I would also try desperately to learn some better time management skills early on, because it's really hard to pick those up later. And there are a lot of things where like I just really wish I'd better balanced my time. But I think that's a challenge that exists throughout life for all people. So I don't know, but maybe I would have been able to get some habits that would serve me well in the future. I'm not sure. I feel like I balance a lot of things and I don't always do a good job of that. And it would be nice to be better at it.
One last question for me. Is there anything in particular that you're really excited about scientifically or personally or professionally or all of the above?
Yeah. I don't know. I mean, scientifically, I'm excited by what these new observational programs are going to show us. So the space telescopes that are coming up, the Square Kilometer Array, the radio telescope array that's going to show us a lot about the first stars and galaxies. The Vera Rubin Observatory is going to show us, it's doing a survey that's going to show us like 1 billion galaxies and 1 million supernovae, something like that. Like we're going to get a ton of data, and then we're going to have much better maps of the universe than we ever did before, and that's going to be exciting. And gravitational waves are a huge, huge deal, and I'm very excited to see where that goes. I'm not specifically working in gravitational waves myself, but I think that it's just such an exciting area, and we're going to learn so much about the universe, and it's just astonishing technology. So I'm very excited about that. And personally, I'm excited to move to Canada. I'm excited to live here and start this new chapter in my life.
Have you lived in a place with snow before?
Yes, I have. not quite like this, but yes. I mean, Princeton got snow. I did my grad school there, so I've got good boots. I've got a couple of nice coats. I've got scarves and things. I think I'll make it.
There's a pretty much endless supply of coffee and hot drinks here. So
that's true. Yeah.
Well, we're so excited that you are going to be joining us at Perimeter very soon, and we're really grateful that you took the time to chat with us.
Thank you so much. Yeah, this has been really great, and I'm excited to become part of the Institute.